In the previous section, we have seen how we can easily turn counting into calculating probabilities by simply applying the formula of the number of desired outcomes divided by the number of total outcomes. In this section, we're going to see another way to calculate probabilities and to support it with a visual representation of a tree diagram. Tree diagrams are useful for experiments that consist of a sequence of steps where every step has multiple options that can then each be represented with the so-called branch of a tree. Let's actually explore it through the example. This is, in fact, the best way to learn. Suppose we have an experiment that consists of selecting 2 cards from a standard deck of 52 cards. We're going to draw cards one after another without replacement. So I'm going to draw a card from the deck, and I'm going to keep it in my hand, and then I'm going to draw another card from the hand. What we're going to note is whether or not the card selected at step 1 and then at step 2 is a heart. For those of you who are not familiar with a deck of cards, heart is one of the suits. So there's 4 suits altogether: hearts, diamonds, spades, and clubs. Here, we're going to be only interested in whether the selected card is a heart or not. Let's start by constructing a tree diagram for this experiment. So I'm going to start by plotting a vertex or a point. You can think of that as the root of your tree. Now, mathematical trees tend to grow actually downwards or to the right, so you're going to have to adjust your biological understanding of the trees here for a second. My first step is to draw a card from a deck of 52 cards and to note whether it's a heart or not. So I have 2 possible outcomes here. I can draw a card that is a heart, or I can draw a card and it will turn out to not be a heart. My hearts, I'm struggling here. There we go. What are my options after that? So let's say I have drawn a heart. I am supposed to draw another card without replacement. So at this step, I'm going to draw another card, and it again might be a heart or not. So after the first step, I'm going to proceed to the second step, and my options are actually the same because I'm observing the same type of phenomenon here. And similarly for my second choice here, if my first card was not a heart, I'm still going to draw the second card, and I have 2 options for the second card. It can be a heart or not. So my tree drawn from the root, so this is kind of like the root of the tree, and these are my branches, okay? As drawn from the tree has a certain number of levels. At the first level, so from the start to the first 2 choices, this is my first card choice, right? So this was my first card, and as the tree keeps going, the experiment sort of takes the next step. This is why it's a sequence of steps. So at every level of the tree, you're going to have the next step in your experiment. The first level here corresponds to the first card choice. The second level here corresponds to the second card choices and options. Now, the thing that is still missing from this tree are actual probabilities. I know how many cards there are in a deck, and I in fact know how many hearts there are. So in terms of hearts, there's 13 hearts in a deck of cards. As I said, there's 4 suits altogether. There's 13 of each suit, which makes up the total of 52 cards. So the last thing I'm going to do on this tree diagram is actually label my branches, all of them, with the corresponding probabilities. So what is the probability of drawing a heart as my first card? And this is again where I'm going to go back to my number of desirable divided by the number of total as the formula. So I start off with a full deck of 52 cards. What is the probability of drawing a heart? The number of hearts is 13, so that's my desirable outcome, and the total number of cards is 52, so that's my total. So the first probability of drawing a heart is 13 out of 52. 13 out of the 52 cards are going to be hearts. I'm going to have to label all of these branches. So I'm going to have to think of all of these possibilities. So let's do the second one here. What is the probability of drawing not a heart on the first card? If there's 13 hearts in the full deck of cards, then there are 39, which is 52 minus 13, non-hearts. So of all the other 3 possible suits. So we're going to apply the same formula again. The probability of drawing a non-heart is 39 out of 52. So I can label this branch with 39 out of 52. Excellent. Now I have to label all of my second card branches. So my first card was a heart. If my first card was a heart, first of all, I now have only 51 cards remaining in my deck because, again, we're drawing without replacement. And at this point, I only have 12 hearts left available because I've already drawn one of them right here. So if I've drawn a heart and I want to draw another heart, I only have 12 hearts left and 51 cards remaining in my deck. If I have drawn a heart and want to draw a non-heart, then there's still 39 available non-hearts and 51 cards in the deck. And we proceed the same way through the other 2 branches. If I have drawn a non-heart first, then on the second card, all of my hearts are still available. So I still have 13 hearts in my deck, but I now only have 51 cards left because I have actually taken a card. And then finally, if I drew a non-heart, that means that instead of 39 non-hearts, at this point, I only have 38 available and 51 cards in a deck. Excellent. A couple of things to notice about this tree diagram now that we've constructed it that will be true of all the tree diagrams ever. Because at every single point, you're listing all the possible outcomes to the experiment, that means that these probabilities add up to 1 because they add up to everything that is possible. And we will notice that on all the branches. So from here, this adds up to 1. And if you look at any node or any vertex going forward, if you include all the possibilities going forward, they should add up to 1. So this adds up to 1, and this adds up to 1. Because once again, from here on, we're covering all the choices with our branches. And all the choices means the probabilities have to be 1. So this will add up to 1, adds to 1, and this will also add to 1. Okay, once we have drawn our tree diagram, we can do a lot of calculations using it directly. So let's see what some of the questions here ask us about. Notice that the diagram has to represent the entire experiment, and then no more diagrams are going to be drawn for every question separately. We're just going to have to interpret this diagram as we go along. Alrighty, I removed a couple of the adds to 1 from the picture just so that it's not as crowded and we can carry on. These are not the standard part of your tree diagram. These were just for observation purposes and for double checking yourself. If you ever find that your branches do not add up to 1, you are in trouble. Okay, so let's get to it. What is the probability we draw 2 hearts? So we have to find a path in our tree that goes through 2 hearts. So that's our diagram is not that big, so I can notice that if I draw heart first and I draw heart second, this branch is going to correspond to my 2 hearts. So the branch here is the one that I'm after. And then all I have to do is multiply the probabilities of the branches along my path. So here I have 13 over 52 times 12 over 51. And that is going to be my total probability. 13 over 52 for the first branch, 12 out of 51 for the second branch. Now, as you notice, this is of course exactly the same as just applying the multiplication principle to the original problem. The way to draw 2 hearts is one after the other, is to draw a heart first, which has the probability of 13 out of 52, and to draw the heart second, which has the probability of 12 out of 51. The diagram allows you to capture all the cases. So if you have more than one question about the same setup, the diagram is going to be a faster way to go. All right, what is the probability we draw exactly 1 heart? So what are my branches here? The way that we can draw exactly 1 heart is a heart and then not a heart. So this branch corresponds to exactly 1 heart. And the other way to draw exactly one heart is to do not heart followed by a heart. So this branch, I'm going to label it on the right-hand side here so I don't, again, make my diagram overly complicated. That's the second branch that corresponds to it. So this way or this way. Remember that or means that only one of the cases, if or means that only one of Notice that in this case, or means only one of these cases can happen. We can draw a heart followed by non-heart, or we can draw non-heart followed by heart. Those cannot happen simultaneously, which means that this will be the additional principle. Okay, so our first branch here, the heart followed by non-heart, I'm going to record the probabilities that occur along the way. So 13 out of 52 times 39 out of 51. So this is a way to draw heart followed by non-heart, or make it clear that this is an or I can have another branch here that results in exactly one heart as well. So 39 over 52 times 13 over 51. Okay, so we multiply along the branches and we add branches together. Okay, multiplication principle within, addition principle on the outside. Next up, what is the probability the second card is a heart? The second one is a heart. So what I need now is to look at where are my options for the second card being a heart. So I'm only really looking at here. I can see that it's a heart here and it's a heart here, which means that now these are the two branches I have to follow along. So I have to follow along this branch, or I have to follow along this branch, because in both of those cases, the second card is a heart. And again, I multiply along the branch and I will add different branches together. So in this case, sorry, I can't keep both the diagram and the answer on the same page here. I will have 13 over 52 times 12 over 51. This corresponds to my first branch. And the second one, so I'm going to add the numbers that correspond to the second branch. 39 over 52 and 13 out of 51. Plus 39 out of 52 times 13 out of 51. All right, next up. See how the diagram is useful already? I've been able to answer 3 questions with the exact same setup, and it's going to carry on like this. What is the probability the second card is a heart if the first one is a heart? So I am given additional information here about the first card. This question only asked what happens, how often does it happen that the second card is a heart? This one asks the same thing, but with additional restriction that the first one is also a heart. This is where we are going to get to generalize our formula of the desired outcome versus total outcomes. I'm going to think a little bit. What are our total allowable outcomes now? What is my space that I am looking for the total of? I am asked what's the probability that the second card is a heart. That's my very specific desired wish. But my total outcomes are the possibilities for when the first card is a heart. So in making this a little bit more explicit, the total is first card is a heart, and the desired is the second is a heart as well. So the desired outcome is first one is a heart and second is a heart. So notice here, of course, that this repeats itself, and that makes sense because this has to appear within my total. My desired is more restrictive, so first one has to be a heart, which is a part of the total, and something else must happen. But the total is all the possible ways where the first one is a heart. Now notice that the top one here, first is a heart and second is a heart, is something that we've already computed in part B, because this is the only way we can draw two hearts. So the top of this fraction I can fill in right away. 12 over 51, there we go. The bottom, we are going to look for when the first card is a heart. So we have to follow the branches when the first card is a heart. It can happen here and it can happen here. And those are the probabilities that we're going to include. So 13 over 52 times 12 over 51, which is of course our already existing choice, or we can follow the second branch of 13 out of 52 times 39 out of 51. So let's record that. So again, I'm going to repeat exactly what's in the numerator here, because my top choice is a subset of my second choice. And then I also have yet another possibility of having the first card as a heart when my restriction on both of them being the heart doesn't actually hold quite yet. So what was it? 13 out of 52 and 39 out of 51. 39 out of 51. And there we go. I encourage you to pause the video here and try to figure out part F by yourself. It's very similar to part E in logic, but slightly different in calculation. Okay, let's go through with this one. What's the probability the first card is a heart if the second one is a heart? So again, we're going to have our generalization of desired versus total. But now my total is given by the restriction. The second one is a heart. So my denominator is going to be all the options when the second card is a heart, whereas my top one is going to have both the first one is a heart and the second one is a heart, which again, not only is the same as in part E, but also the same as we've computed in part B. But let me write it out. First is a heart and second is a heart. Okay, so now copying over what we have for the numerator, 12 over 51. The one thing I noticed though too is that what I have in the denominator, the second card is a heart, is something we've computed in part D. So I can simply take this answer and copy it over here. Okay, no need to redo the work that we've already done. And the same pattern holds here. Notice that my answer on the top is a subset of the answers of the bottom because my desired outcomes are always a subset of my total. So I should see my desired outcome as one of the ones in the total plus some other stuff that I did not want. Let's consider an example for something that is clearly in the news today. The PCR tests and how accurate they are in detecting COVID-19. So my data is drawn from Public Health Ontario because they actually track false negative and false positive rates for PCR tests. We are going to take their numbers as numbers that we're going to work with. We're also going to make an assumption that about 10% of the population at any point in time, basically from now on, given that it's an endemic, will have COVID-19. Let's say Amanda is having symptoms and tests positive. What is the probability that she actually has COVID-19? We know that the tests are not perfect, but how imperfect are they? So first of all, let's discuss the terminology of false negative and false positive. False negative, although it sounds like it's an easy concept, sometimes get very confusing, means that the test is negative. So the PCR test that you took is negative, but the result is actually wrong. So the test produces the negative, but it's a false result. So the test is wrong. Similarly, I'm actually gonna be a little bit lazy and copy this over. False positive means the exact same thing, but in the reverse. So false positive means that the test showed you that you are positive for COVID-19, but the test is wrong. So these are indication of what the test result shows, and the false means that that is actually incorrect. So let's construct a tree diagram for this situation. At the first vertex, we're going to actually specify the condition. So a person has COVID or does not. Okay, so my first branch here, let me label it right away, will correspond to the condition. COVID, let's say not COVID. C, let's say not C. Okay, I am assuming that 10% of the population has COVID. So now I can actually assign that percentage to the branches. 10% of the population has COVID means that 10% should actually have the probability 0.1 here, and 90% of people do not have COVID. So 90% of the people should belong to this branch. Now, after that, we're going to have branches that correspond to the actual test results. So the test either is positive or it's negative, and that's going to be true of whether the person has COVID or not. They will either test positive or negative. So again, let me label the branches right away. Test results. Okay, so test result, of course, depends on whether or not you have COVID, but is not perfect. So there will be some discrepancy in it. So where do false negative and false positive belong? Again, false negative means that you have tested negative, but the test is wrong, which means you actually have COVID. You've tested negative having COVID. So you have COVID, but you've tested negative. This right here is the branch that corresponds to false negative. Let's actually label that false negative right here. What about false positive? That means that the test is positive, but the test is wrong, which means you don't actually have COVID. So not having COVID, but testing positive is right here. This is the branch that corresponds to false positive. Now, the good news is that we can actually label both of those branches now. So the false negative rate is 15%, which means that this branch will be labeled with 15%. And the false positive rate is 2.5%, which means that this branch now has to correspond to 2.5%. Now, you notice that I don't actually have labels for the other two branches yet. And that is something that we can fill out by using the structure of the tree. So remember that from every vertex or every node, the sum of outgoing edges should always add up to 1. So if this is 15%, then what we have on this branch must be 0.85, so that altogether these two branches add up to 1. And similarly, I've managed to label false positive because that is the information I have. I don't have the information for this branch, but I can figure it out by simply saying that what belongs on this branch is going to be 1 minus the number there. And you know what? In fact, I'm actually going to leave it like that because I want to actually show where this arithmetic takes place and how we can actually calculate those numbers. Once we have that, we're going to be able to answer any question regarding what is the probability of a person actually having the test, depending on how prevalent the disease is in the population and how accurate the testing is. So Amanda has tested positive. If she's tested positive, it means that she is in one of these branches. So let's actually highlight them. She's tested positive. Either if she has COVID and tested positive, which is this branch, or she doesn't have COVID, but she tested positive nonetheless because the test is wrong some of the time. What is the probability that she actually has COVID? So we're gonna, again, employ our desirable versus total. So my total here, of course, are all the possible branches, because she has tested positive, and therefore that's my total. So my total is going to be following the positive branch along. So 0.1 times 0.85. So she could have COVID and test positive, or she could not have COVID but test positive nonetheless. So 0.9 times 0.025. What goes on top, though, is where we're actually asked. What is the probability she actually has COVID? And only one of these branches corresponds to her actually having COVID, which is this first one here. So 0.1 times 0.85. And once again, we notice the same structure. What happens on top occurs as one of the summands at the bottom because the top is a subset of all the possibilities on the bottom. Now, if you calculate this, you will actually find out what is the probability that she actually has COVID. This question, of course, can be taken again and again. So for example, in order to produce more accurate results, sometimes the tests are taken twice. So think about how we can expand this setup, this tree diagram, and this logic to figure out what is the probability Amanda actually has COVID if she tested positive 2 times in a row. Now let's take a look at another example. So here we have 5 working light bulbs and 2 defective ones all mixed in within the same box. Suppose we reach into the box and select a bulb at random and test it. If it's defective, we discard it and try another light bulb from the box. So if the bulb doesn't work, we basically throw it out and then get another one from the box. We repeat this process until we eventually find 2 working light bulbs. Let's build a tree diagram illustrating this scenario. So what happens and how many steps do we have to take? So as before, I'm going to start off with, this is just being me, standing in front of a box full of light bulbs. It happens to everybody occasionally. I'm going to draw 1 light bulb at a time and test whether it's defective or not. So on my first try, I can have a light bulb that is defective, working, let's say, or not working. So maybe that's how I'm going to label them. Working and defective. Okay, so again, in labeling, this is my first bulb. What is the probability that on my first try, I'm going to hit a working light bulb? The box has 7 light bulbs altogether. 5 of them are working. So 5 out of 7 times on the first bulb, I'm going to hit a working light bulb, and 2 out of 7 times, I'm going to hit something that does not work. And I carry on. If I hit a working light bulb, I'm going to draw another light bulb from the box. And I have, again, 2 choices. I can have a working light bulb or a defective one. What are my probabilities here now? Well, I still have some defective and some working light bulbs in the box. But now at this point, I no longer have 7 of them. I have 6 in total. And because my first scenario here corresponded to drawing a working light bulb, it means I now have 1 fewer working light bulb still available in the box. So here I'm going to have 4 out of 6 choices for a working light bulb and 2 out of 6 choices for a defective one. I'm going to stop the process when I find 2 working light bulbs. So if I follow this branch and I've hit 2 working light bulbs, I'm not going to draw any more light bulbs. So this branch of the tree is done. However, I am going to continue if I'm at this point right here, because I have a working light bulb and a defective one. So I have not yet drawn 2 working light bulbs. So I'm going to carry on and extend my tree further. Again, I have 2 choices, a working light bulb and a defective one, and so on. I encourage you to pause the video at this point and try to fill in the rest of that tree by going through and figuring out what the potential options are. Once we come back, I will have the full tree drawn, but please take a moment to construct it by yourself. Okay, here's my full tree. Notice that this one is quite extensive. I try to always keep the layers about the same vertically so I can distinguish between my actual categories, right? So it's easier to track what happens when the actual picture is a little bit more structured than it could be. Now I've labeled everything except for a few branches here because I actually wanted to take a look and discuss why the labels are going to be the way that they are on them. So if I draw a defective light bulb first and I draw a defective light bulb second, there's only 2 of them. So for example, in this branch, that means that what I have left are all the working light bulbs. So at this point, while there's only 5 left, the probability of drawing a working light bulb is 5 out of 5. Or, if you want to simplify it, is equal to 1. Only working light bulbs are left in the box at that point, so I have no choice but to draw a working one. And at this point too, again, there are 4 light bulbs left in the box, but all 4 of them are working, which means the probability of drawing the working one is 4 out of 4 or 1. So this also stands in line with our rule that if at any point I look forward, the sum along all the branches should be 1, which means that there's only 1 branch, it has to have 1 on it. And again, double checking that this rule actually works on all the branches throughout will be a good other way to check to make sure that your tree diagram is proper. So let's see, once we have that, what kinds of questions we can answer. What is the probability at least one defective bulb will be found? So at least one, where does that happen? Or maybe where does it not happen? So this branch, for example, that does not happen because I drew working and then working. How am I going to figure out how many different ways there are to have at least one defective bulb? At least one defective bulb is quite literally all the other branches. So I can do that directly by multiplying along each and single one of these. What do I have? 5 different branches, and then adding all of the results together. Or I can remember the complement rule. Let's write that down. Probability of at least one defective is the same as 1 minus the probability of no defective light bulbs. The complement rule says that I can compute the exact opposite and subtract it from the total. In probability world, the total is 1, so here's what I have. So while I could add along all the 5 branches that correspond to at least one defective light bulb, I can save myself a lot of work, compute only along the branch that has no defective light bulbs and subtract that from 1. So in this case, the no defective light bulbs is only this branch right here, which corresponds to 5/7 times 4/6. And that's our answer here. We can compute that all together. It should come out to be 11 out of 21. Let's take a look at part C. What is the probability exactly one defective bulb will be found, given that you know at least one bulb has been tested? So exactly one defective bulb. Where does that happen? Exactly one means I am either in this scenario because there is exactly one defective light bulb along this branch. You know what? Let me actually highlight it. So there's this branch right here. Or the other branch that has, so for example, this branch is not going to work because there's 2 defective light bulbs along the way. So the only other one that works that has exactly one defective is this one right here. So I either hit the defective light bulb on the second try and the other 2 are working, or I hit the defective one on the first one, but then the other 2 are actually working. Okay, so what do we have here? We are asked the probability that exactly one defective bulb is found, given that you know at least one is tested. So remember that this given that you know something restricts our domain for totals. So if I am once again thinking of my desirable outcome versus my total outcomes are now restricted by the fact that I know at least one of the light bulbs is defective. And that is exactly what we've calculated in part B. So at least one is defective, goes on the bottom, and my desirable outcome, exactly one defective, goes on top. So exactly one defective. Now, once again, a good common sense check is to double make sure that what's on top is a subset of what's on the bottom. Having at least one defective light bulb means I had at least one defective light bulb and maybe more. Now, the good news for us is that the denominator here, 11 out of 21, has already been calculated in part B, so we can simply rewrite the answer. But for the exactly one, we're going to have to follow through the 2 branches. So my first branch is going to be 5/7 times 2/6 times 4/5. That's my case 1. Or I could have fallen into the second case. So 2/7 times 5/6 times 4/5. Now, because I've done the calculations here differently than following all the corresponding branches, maybe it's not already obvious how that fits within the denominator. So let's think back to part B. The probability of at least one defective light bulb are all of these 5 different branches. And you can see that my 2 highlighted in blue that correspond to part C are of course a part of them, together with the other 3 cases that I did not want. So while it's not obvious in the format, these 2 cases are in fact embed it into the denominator here with some other stuff that I did not want. Let's once again have an example of how we can apply our newly found counting techniques to think about security on the web. I am sure that many of you noticed that a lot of websites now have multi-factor authentication, or sometimes they call it two-factor authentication, where you're asked to enter your password and then you receive a PIN via text or voicemail that you have to plug in into the system as well before it actually grants you access. Multi-factor authentication is yet another way of thinking about layered defenses. There's more than one layer of protective authorization on your way to actually accessing the system. So here's a simple example. Suppose it's you, the user, and in order to access the system, you're going to have to provide a password and a text PIN. And we know that password security, for example, in this particular case, provides about 70% of actual security. So 70% of the cases, your password is going to be safe. So hacker only has about 30% chance of guessing it properly. But then afterwards, they can't access the system quite yet. They also have to enter the PIN. And the PIN, because they're received on your device, provides about 90% of security. Because in order to hack the PIN, the attacker must also have actually had access to your phone or other device. Once we have that, the access will be granted. So the question is, how secure is this system? Now, just like in the case of, once again, this is just an example of a layered defense architecture. What we're going to do is think about what does a hacker have to do in order to gain access here. The only way to gain access in this way is to hack both the password and the PIN code. So what are the chances of that happening? If I'm the hacker, the chances of me guessing the password that has 70% security is 30% of the time I'm going to be able to somehow guess it or obtain it. And then consecutively, so multiplication principle at work here, I have to get a hold of PIN, which is 90% secure, which means in 10% of the chances a hacker is going to be able to get through this. 0.3 times 0.1 is 0.03, which translates to 3%. So within this system, the password being 70% secure and PIN being 90% secure, that means that the hacker is only able to get access 3% of the time, which means that the system overall is 97% secure. Notice how this is bigger than either of the components of the system. So this has an advantage of some aggregate security building on top of each other to produce the system that is more secure than either of its components. Now, we also notice a lot of the times that you have an option of logging into your account directly, or maybe you can press the I forgot my password button and the system will send you to answer security questions that are sort of by design not very secure. So we're going to assume that you can either access the system this way or you can provide answers to security questions, in which case those ones are only 40% secure. So let's copy this system over because we still have this portion of the system. Or instead of going through this way and getting access, this is our one way to do it. The other way to do it is instead, the way to get here is to answer some questions. And again, questions are 40% secure. So here's you as a person answering questions. Okay, what is the security of this system now? Well, now we have two branches of this tree that leads us to the access, right? So remember that we multiply along the branch and we add the two branches together. Our first branch is the same as in part A of this question. So if I'm the hacker, I'll be able to access it 30% of the time through the password and then 10% of the time through the PIN, or I could bypass this and simply answer the questions, which as a hacker, I'll be able to successfully do 60% of the time. So notice that again, thinking as a hacker, you have to take complements of the security measures. So now this results in 0.63 which means that 63% of the time the hacker will be able to gain access. So my system is only 37% secure in this case. And notice a huge difference here. This 37% is less than any of the components. So that means that the entire system is weaker than any of the components separately. By giving access through different ways creates more pathways for the hacker, and if those pathways in particular are weaker than the other ones, it weakens the entire system as a whole. The layered defense approach is stronger, provides a security that is stronger than any of the components. The parallel access approach always weakens the system. For our last example here, I'm not actually going to go through it in detail. I will leave it as bonus work for you. But this is a pretty famous problem. It was part of the TV show. The setup is as following. There are 3 doors. There's 1 car and 2 goats. And you, of course, have no idea where the car is, and you certainly want the car more than you want the goat. The idea is you pick a door, and the host, Monty Hall, will open one of the 2 other doors that you did not choose to always reveal a goat. And the choice is up to you, whether you stick to with your original option or you pick the door that has not yet been opened. So you either stay with your original choice or you switch based on the fact that the host opened the door and revealed a goat behind it. This can be solved using probabilities, and we can actually construct a tree diagram for that as well. So if we decide to label doors, I'll start you off on that, A, B, C, then we as a participant in the show are faced with a choice, which door to open, A, B, or C. And the probability that the car is behind each one of these is 1/3. Only one of the 3 doors has a desirable outcome behind it. And from then on, you can decide whether you would like to stay or you would like to switch to one of the other 2 doors. You can fill out this entire tree, so you will have these exact same 3 options appearing for the doors B and C. And then you can calculate the probability that you win if you stay and the probability that you win if you switch doors. The answer is usually quite surprising, so I strongly encourage you to persevere and make these calculations for yourself. It's a fun problem, and yet again, more practice with probabilities and tree diagrams.